Welcome back to Sine and Cosine the functions, part 8 of 8. We're going to look at how to graph these functions with a calculator. So to create a reasonable viewing window, find the period for the x-axis and the amplitude for the y-axis and adjust accordingly. This is very important to get an accurate graph. If we determine the appropriate viewing window for f of x equals 30, sine of 0.005x in radians, we need to figure out the period which will be the 0.005, which is k, and we'll divide 2 pi by 0.005. So let's see what that gives us. We have 1,256.6. We'll go ahead and just round it up to 1,260. Because remember, this is to help us with our viewing window. It hasn't been shifted horizontally, so I can go on the interval from 0 to 1,260. And then my amplitude is 30, which means my window vertically needs to go from negative 30 to 30. And now I should be able to set up my window. If I go to the window button, I want my x min. It could stay at negative 10 just so you can kind of see how the period continues into the next period. But my x max needs to be 1,260. My y min needs to be negative 30. And my y max needs to be 30. Now that's to only see to the very tip and the very bottom of each one of these maxes and mins in the period. So if you want to be able to see just a little past it, you could say negative 32 to positive 32, just so you have a little bit of a buffer between the edge of your graph and the edge of the window. Now let's enter the function in. 30 sine of 0.005 x, close parenthesis, and then graph it. This is a beautiful picture of one period for the sine function, given our information about how it's been shifted and stretched and shrunk, etc. But I want to point out something else. Notice that these horizontal and vertical axes are very bolded. That's because the way we have broken them into pieces are so close together, it's not showing the notches anymore, it's just all the notches stuck together. One way to fix this is to look at the intervals for which your notches exist. So if we're in radians, let's go back to our window. We're doing steps in the x direction of 1. That means we have 1,260 of those steps. So let's change that to maybe 2 pi. And when we put 2 pi in there, when we recalculate it, it's going to actually go to a decimal. But at least it's a repeating decimal that's fairly accurate. Now let's see what it does. So now you can see what pi's would look like in the vertical direction, which doesn't necessarily make a ton of sense. Let's say maybe every 10 in the y direction. So if we make our scales in the y direction be 10, and see how that changes, we can see that there are 3 of them, which makes sense. And then because we have broken our sine curve up into large chunks for each period, let's see if we can think of maybe a value that would be better than 2 pi, because you can see that the scale here is still smushed together. So let's make our scale in the x direction be 200 pi. And let's see what that does. Very nice. So you can see how it crossed. So if you're curious about whether you got your scale right when you are looking for a period of a function, you can scale your x-axis to have notches specifically where you want them, which is pretty cool. So when you're asked now to graph, I'm going to clear the previous one, we're asked to graph y equals sine of x, y equals 2 sine of x, and then y equals sine of x plus 2 sine of x. Hopefully by now in your math journey, you realize that since this is 1 sine of x plus 2 sine of x, this is equal to 3 sine x, and all it's going to do is change the amplitude. But it might not have been obvious, and if that's the case, just practice this a little more. You'll get the idea. If I graph sine of x and then y equals 2 sine of x, we will need to change our window substantially. The amplitude is 2, so to graph all of them, both the sine of x and 2 sine of x, on the same graphing window, we need to change our x dimensions from 0, and I'm going to just keep it at like -1 so I can see a buffer region on both sides, and that's pretty common. So x min is -1, x max is going to be, let's just say 3 pi, because I want to be able to see past 1 period. I could just go from 0 to 2 pi, but that's not going to show me kind of the context in which the sine of x is graphed. I'm going to make my scalars be pi over 4, because if I do that, I can see all the critical points, the equilibriums, the maxes, the mins. And then my y min will be a -2. But since I want a buffer, again, I'm going to be making it -3. And my y max will be 3. My y scalar, I'll just go with 1. And now I should be able to see my graphs nicely in this window. So sine of x will be my first graph that I put in. And the next one will be 2 sine of x. And I'll graph that one. I'll graph them both on the same curve. So this is just sine of x that we see. And there is sine with an amplitude of 2, the higher one. Now if you were to graph sine of x plus 2 sine of x, that's going to be 3 sine x. And we can graph that one as well. So the vertical stretch occurs when you add 2 of these functions together, as long as their guts match, and in this case they do. I also want to point out that you can see here that the maximums and the minimums are at intervals of pi over 4. So here's pi over 4, 2 pi over 4, or just pi over 2, 3 pi over 4, 4 pi over 4, 5. You get the idea. It's so convenient to be able to set up your own scale.